Ladies and gentlemen, thank you for staying with us. The next lecture is held or given by Dr. Ioanna Giouroudi. Ioanna is finished her master degree studies in engineering in the National University of Athens. Then she studied PhD at the Technical University in Vienna, Austria. She was a PhD student of Professor Hans Hauser, who was a big name in the development of magnetic sensors and who unfortunately passed away several years ago. And after she finished her PhD, she went for postdoc for 2 years to South Africa. And after that, she returned back to Vienna to teach there as university assistant, which is the official name of her position. So, Ioanna, welcome. Thank you for coming. And
thank you very much.
Room is yours.
Thank you very much for coming. Today I will talk to you about magnetism and basically some general fundamentals of magnetism. A little bit of the history, how magnetism has been found in astrophysics, and as I say, the fundamentals. And then I'll just talk about the magnetic states of matter, which is all the different phenomena being observed in magnetism. Diamagnetism, superconductivity, paramagnetism, ferromagnetism, superparamagnetism, ferrimagnetism, and antiferromagnetism. A little bit about the history of magnetics. The term magnetism comes from the ancient Greek city, of course, of Magnesia. I skip the Chinese because I'm Greek, so I promote the Greek part of magnetism. And Magnesia was a place in which many natural magnets were found. And we refer to these natural magnets as lodestones, and they contain magnetite, and this is a natural magnetic material. It's an oxide ferrite, and this was what used to be used at the beginning in navigation and in compasses. Now, in 1600, William Gilbert first proposed that the Earth itself is a magnet, and he predicted that the Earth would be found to have magnetic poles. What was suggested is that the Earth exerts magnetic forces, and it is surrounded by a magnetic field, as you can see here, that is strongest near the North and the South Pole. Sometimes it is known that the Earth's magnetic poles flip, and this happens every 500,000 years or so. And of course, we use the Earth's magnetic field in order to find direction in navigation. Now, the needle of a compass, you have to keep in mind, always points towards the magnetic South Pole. And we call this direction north because opposites attract, and this is how we navigate with all the magnetic sensors we are currently using. Please keep in mind that we have a geographic North Pole, and the north end of the axis around, this is the end of the axis around which the Earth rotates. So you see here the rotational axis, and this is the geographical north. And the magnetic North Pole is the point of the Earth to which a compass needle will point. So in 1819, Ørsted showed that the magnetic effects could be produced by moving electrical charges. And afterwards, Faraday and Henry in 1831 showed that the electrical currents could be produced by moving magnets.
Is it known why these poles of Earth switch, or why they?
No, we have astrophysics here. No, I personally don't know, but I'm sure there has been a lot of research behind it, why they flip. and I'm an electrical engineer. I think we can talk to astrophysics about this. So what is now magnetism? Magnetism is the force of attraction or repulsion of a magnetic material due to the arrangement of its atoms, and especially the electrons. We have to keep in mind that all magnetic phenomena will result from forces between electrical charges which are in motion. So when electrical charges are in motion, they produce magnetic fields. Ampere suggested in 1820 that magnetic properties of matter were due to tiny atomic currents. So within the atoms, electrical currents are being produced, and this is the reason for magnetic properties of matter. And all atoms will exhibit magnetic effects. The medium in which charges are moving has profound effect, of course, on the observed magnetic forces. So what happens is that we have a moving charge, and this sets up in the space around it a magnetic field. And it's this magnetic field that will exert a force or on any other moving charge through it. Keep in mind that magnetic fields are vector quantities, so they have a magnitude and a direction. Okay, a little bit now, some more general and interesting information about magnetism. The sun also has a magnetic field, and it extends far above the sun's surface. And also, it has been proven that other planets in the solar system have these magnetic fields. Now, a fundamental property of magnetic fields is, as I said, is that they exert forces on moving electrical charges. So if we have a magnetic field, it can trap charged particles, such as electrons or protons, as they are forced to execute as a spiraling motion back and forth along these field lines. Yeah, so they move like a spiral. And if a charged particle moves at an angle to a magnetic field, then the magnetic force which will act on it, it will cause it to move in this spiral direction around the magnetic field lines. So as it is illustrated in this figure, the charged particles are reflected at these mirror points, and the field line is the point where the field lines come close together, and the spirals then become more tightened than further away from these mirror points. And one of these early space exploration was the discovery in the late 1950s that the Earth is surrounded with two regions of particularly high concentration of charged particles, and that are called the Van Allen radiation belts. Well, I'll explain a little bit later. So the primary source of these charged particles is the stream particles which emanate from the sun. And we call this the solar wind. I will show you later the charged particles which are trapped in the Earth's magnetic field are responsible for some phenomena we observe in the northern and southern hemispheres, which are called auroras, but I will explain this later. So the field lines defining the structure of the magnetic field are similar to these of a simple bar magnet. So you can imagine like having a simple bar magnet as it's here illustrated, and that's how the field lines, you can imagine the field lines being similar to the field lines of a bar magnet. As I mentioned before, the axis of the magnetic field is tipped with respect to the rotational axis of the Earth. So the true north, which is defined by the direction of defined by the direction to the north magnetic pole, to the north rotational pole, does not coincide, keep in mind, with the magnetic north. So therefore, the direction in compass has to be corrected by fixed amounts at given points at the surface of the Earth in order to yield true directions. Now, the Earth, as I said, the Earth's magnetic field extends into the space, and this is called the magnetosphere. Now, the solar wind, it's a stream of mostly charged particles which come from the sun, and they travel out past all the planets in the solar system, and this is what we call solar wind. And please keep in mind that this is not like the wind on Earth. It is electrically charged, and it will therefore interact with magnetic fields, yeah? Not like the wind on Earth, which is neutral. So as the solar wind is bombarding the Earth's magnetic field, these particles are found in two large regions, and these are the Van Allen belts. And sometimes these charged particles will penetrate this field. And what happens then? When the solar wind strikes this magnetosphere, we see this phenomenon called the aurora borealis in the northern hemisphere and the aurora australis in the northern hemisphere. Aurora was named after the Roman goddess of dawn, and borealis from the Greek word boreas, which is a north wind. And australis is the Latin word of the south. It means of the south. And this, since this aurora is only observed on the southern hemisphere, that's how I took this name. So this aurora australis is detectable from latitudes in Antarctica, South America, or Australasia. So now it's typically red or green light, and you can see the nearly vertical lines of the which trace the Earth's magnetic field lines. We have two misconceptions about auroras, and one is that they are caused by reflection of water or of ice particles in the atmosphere. And the other misconception is that the solar wind particles directly cause most of the auroras. And neither of these ideas is true, and I'll describe you the most recent understanding of how auroras are being formed. And this most recent understanding is that they are caused by electrified, by charged particles coming from the Earth's magnetosphere, hitting the Earth's upper atmosphere, and then it makes it glow. And you see this incredible phenomenon. So, as I say, particles that cause auroras come from inside the magnetic cavity, and these charged particles inside the magnetosphere come from the solar wind and from the charged particles in our upper atmosphere, which is called the ionosphere. And the ionosphere is mostly created by the sun's light, which hits the upper atmosphere, and we get absolutely observed and separating the atoms from the electrons from the atoms. And this leaves a positively charged ions and electrons moving around the atmosphere. And then these particles can escape to the magnetosphere. Now, how do the solar wind particles enter the Earth's magnetosphere if they are all deflected? The recent explanation or scientific research field is that a lot of scientists believe that this is related to the interaction of solar wind with magnetic fields and the Earth's magnetic field. And this interaction causes this magnetic reconnection region, which basically opens a small door for the particles to move from the solar wind inside the Earth's magnetosphere. So this is what scientists believe that is happening, and this is how solar wind can enter the Earth's magnetosphere. Now we have a little bit, in order to understand about what kind of orders of magnetic fields we're talking about. You see in the sun surface, we are talking about 10 power minus 4 Tesla. At the Earth's orbit, we're talking about 5 times 10 power minus 9 Tesla. A neutron star, which is a type of stellar remnant that results from a gravitational collapse of a massive star, has a field of about 10 power 8 Tesla. And a magnetar has the strongest known field so far. A magnetar is a type of neutron star that has an extremely powerful field, as I showed you, but it is very difficult to study this because they are very far away from the Earth. They are about 20 kilometers in diameter, and they have a greater mass than the Sun. But it's very difficult to study them. And then we talk about the galactic field, which is very, very low, 10 power minus 10 Tesla to 10 powers minus 9 Tesla. Just to get an idea of which orders we're talking about when it comes to magnetic fields in the solar system. Now let's come a little bit to the fundamentals of magnetism and what causes the magnetic fields. As I said, the matter is made of atoms, and the positively charged center is the nucleus, and it's orbited by one or more negatively charged particles, which are the electrons. And as the electrons, the electrons also spin as they travel around the nucleus, so you can imagine the same as you having the Sun and the Earth orbiting the Sun and the Earth spinning around itself as well. It's similar in the inside the atoms, and as the electrons spin, so you can see it here, as they spin and orbit the nucleus, then they produce a magnetic field. And the direction of the spin and the orbit determine the direction of the magnetic field. And keep in mind that the strength of this field is called the magnetic moment. So all the electrons will produce a magnetic field as they spin and they orbit the nucleus. But in some atoms, we have 2 electrons spinning and orbiting in opposite directions, as you can see here in a helium atom. And this opposite direction will occur up, and the net magnetic moment of the atom will be 0. So the direction of the spin and the orbit of the electron will determine, as I said, the direction of the magnetic field. And in most materials, electron pairing occurs, so we don't have. That's why not all the materials are magnetic. Niels Bohr in the early 90s proposed that the electrons will give or take energy only when they change their energy levels. So he suggests that there are energy levels, and when the electrons move up, they take energy, and when they move down, they release energy. And this energy itself is released in packets which are called photons. An electron which is not in its native energy level always has to fall back to its original stable level. And this is what Bohr suggested. As long as electrons stay in these energy levels, they are stable. I won't go too much in detail and in maths. I will just try to simplify how magnetism works. So you can consider a permanent magnet. You've all had contact with permanent magnets, and it exerts a force on another magnet through space. And this force field is, in fact, the magnetic field. So the same can be observed if you have a current through a coil. And here you can see the equivalence between a permanent magnet and a coil. So the same way that you have a magnetic field around a permanent magnet, if you have a coil and you send a driving current through it, you also have this production of this generation of magnetic fields. So a loop of electrical current generates a magnetic dipole field equivalent to a permanent magnet. Just a little bit of the laws of magnetics. We have the Biot-Savart law, which says that a current, if you have a current conducting wire, it will induce a radial magnetic field. And we have the Ampere's law that says if we have two wires which carry parallel currents, they will magnetically attract one another, similar to permanent magnets. Now, if you have a mobile charge that has a charge of Q and it moves in a current-carrying conductor, so in a wire, for example, it experiences two kinds of forces. And of course, there are the electrical forces which act upon the charge in the presence of an electric field, and you have magnetic forces which act on the moving charge in the presence of a magnetic field. And this is the Lorentz force. So you have the magnetic force and the electric force acting on the charge which is moving through a conductor. Now, a little bit about the terminology in the most easy possible way. The strength of the magnetic field is usually given by the magnetic flux density, and we measure this in Tesla. And this we also call the magnetic induction. So if you consider a coil that has a cross-sectional area A, and you place it in a uniform magnetic field, then you have this magnetic flux density B, and is given is the magnetic flux per unit area. So you have this equation where you have phi is the magnetic flux given in Weber, B is the magnetic field strength or magnetic induction, and just to get an idea, 1 Weber is 1 Tesla per meter squared. Now, if you have the plane of the coil and is at an angle theta to the magnetic field, then the vector component will be given through this equation. We shouldn't mix the induction with the intensity, so the magnetic field intensity is given in ampere per meter, and the relation between the two is very simple, where μ0 is the permeability of vacuum, and permeability is basically a measure of the ability of a material to convey a magnetic flux. So permeability is a measure how a material conveys the magnetic flux. So we have μ0, the permeability in vacuum, and the relative permeability, which is of the medium in which the relation holds, yeah? So between medium and that of vacuum. Now, how do we define the direction of the magnetic field? Because as I say, it's a vector, yeah? So it is defined as the direction of motion of a charged particle on which the magnetic field would not exert a force. So this is how we can define which direction the magnetic field is going to have. And the magnitude of the B vector is proportional to this force, which acts on the charge that moves inside the conductor. And it's given, as I say, in Tesla, or 1 Tesla is 10,000 Gauss, just to get an idea of all the entities that we're measuring. Yeah, some typical magnetic flux densities, I won't go into detail, but just to see, like, the magnetic storage media is -1 millitesla. You have magnetic flux in interstellar space, 100 picotesla, and the lowest magnetic flux, which has been achievable in carefully shielded rooms, is very, very low. And as I say, in the surface of a neutron star is about 100 megatesla. Of course, there is an equivalence between a magnetic circuit and an electric circuit. So in a magnetic circuit, you have the magnetic field intensity, which is given in amps per meter. In an electric field, you have volts per meter. This is just a little bit to see how the two can be related to each other. You have the magnetic flux, and you have the current, and you also have the permeability in a magnetic circuit, and in an electrical circuit, you have the permittivity. Let's go now a little bit in more terminology in magnetics. You all with me still? Good. I'm glad. So what is magnetization, yeah? It is a measure of how a material responds when a magnetic field is applied to it. So you apply a magnetic field to a material, and the way it responds to it is given by the magnetization. And it also describes the way that a material will change its magnetic field. So you have a material, you bring it into a magnetic field, and the magnetic field will change. And this is also depending on the magnetization of the material. What causes this magnetization is the origin of the magnetic moments, yeah, which are either macroscopic electrical currents, as I showed before. They are caused from the motion of electrons in atoms, or the spin of the electrons or the nuclei. So these are the reasons that cause these magnetic moments, and magnetic moments are responsible for magnetization. It's not always homogeneous within a body, but it rather differs between different points. How do we define it? A little bit easy maths. As the magnetic moment per unit volume of a solid, yeah? And this is the relation between magnetization and induction. So the magnetization and the magnetic field will contribute to the magnetic induction in a similar way. This is what we have to keep in mind. Now, as I said, how does magnetization arise in materials? Either from unpaired electron spins, or from the orbital motion of the electrons within the material. But this is to a lesser extent, mostly is because of the unpaired electrons. As I showed to you, if you have paired electrons, they cancel each other, so you have no magnetization inside your material. But if you have unpaired electrons, then magnetization is being caused. And it's dependent on several parameters. So imagine this is your material. As I say, it's the magnetic moment per unit volume within the material. So it depends on the density of the magnetic dipole, how dense it is, or how not dense is it. Depends on the magnitude of the magnetic dipole, and also on the arrangement within the material. Now, how are these three terms related to each other? So you have the magnetic inductions, and this consists of two contributions. One from the magnetic field and one from the magnetization. In the free space is given by μ0 times the field intensity. But when a magnetization of a material contributes to the induction, is given also by the same equation. So what we eventually have is that the induction equals μ0 times the field intensity plus the magnetization. And the field, as I say, is generated by electrical currents outside the material if you have a solenoid or an electromagnet or a permanent magnet. And the magnetization is generated by the resultant spin or the orbital momentum within the solid. So the field is generated externally, magnetization is generated internally. This is what we have to keep in mind. And now, how does this material respond to an applied magnetic field? So you have here the magnetic field, the externally applied magnetic field, and you have the magnetization. And we measure this, how easy the material which can be magnetized is given by the magnetic susceptibility. And it's given by this equation, or the slope of the magnetization versus the applied magnetic field. So just remember, susceptibility is a measure of how easily a material can be magnetized. These are now the correlations, how permeability and susceptibility and been related to each other using this formula. Now, how does magnetization respond to the applied field? There is a variety of ways, but it usually depends on the type of material you have and also on the temperature. And you can see here, again, a magnetization curve for different temperatures. Usually it's non-linear, but magnetization tends to saturate at high fields and at low temperatures. So this is how you can have the response between magnetization and applied magnetic field. Yeah, I'm not going to go a little bit to the conversions. So far clear? Can I proceed to the states of matter? Thank you. So we have, as I say, different states of matter. And the first phenomenon I will show you is called diamagnetism. And a diamagnetic material has a very low permeability, lower than the unit. And remember, permeability is a measure of the ability of a material to convey magnetic flux. It also has a susceptibility around the -10⁻⁵, and this is a measure of how easily the material can be magnetized. So what happens in a diamagnetic material, it will oppose the applied magnetic field. And such materials is copper, silver, gold, and other materials, but these are the most commonly known. And these diamagnetic materials are used to design mechanical parts that should not disturb the magnetic field that it is to be measured. So if you have to design mechanical parts that should not interact with the magnetic field that is being measured, you use diamagnetic materials like these ones. These are, in general, materials that have all their electrons paired, and they have no net magnetic moment. So we call them diamagnetic materials. So if you place them in a magnetic field, they will produce a slight magnetic field, and this magnetic field will oppose the main magnetic field being applied. If you take a bar magnet, both ends of it, they will repel diamagnetic materials. And here, like, there's a small schematic. What happens inside of a diamagnetic material when you apply a magnetic field? Keep in mind that anything that has water in it is diamagnetic, and the key concept is that diamagnetic materials were opposed to an applied magnetic fields, and both ends of a magnet will repel these diamagnetic materials. A phenomenon that evolves from diamagnetism is superconductivity. And Heike Owens in 1911 discovered this phenomenon, and he discovered that at exactly zero electrical resistance will occur at certain materials below a characteristic temperature. So when you have some materials that are cooled down below a critical temperature, they will become perfect conductors. And these are called superconductors. And then the magnetic field inside them will vanish regardless of any external field. So the fact that this resistance is zero, it has been demonstrated by sustaining currents in superconducting rings for many years, and you had no measurable reduction of the you had no measurable reduction of these currents. So if you induce a current in an ordinary metal ring, it will decay rapidly, yeah? But if you have a superconducting ring, it has exhibited a decay constant for over 1 billion years. So you can use superconductors and the current never decays. So a little bit about the physics. You have the effect called Meissner, is the expulsion of a magnetic field from a superconductor when it transits the superconducted state. So you see here the applied field. Here you have a normal non-superconducting material, and here you have a superconducting material. After a critical temperature, it remains, you give a current, and then it persists on your superconducting ring. So it's cool, and keep in mind that it's cooled in an external magnetic field. So this critical temperature is the temperature at which the electrical resistivity of the metal will drop to 0. You can see a little bit the comparison if you have the resistance here and the temperature. This is for a superconductor, and for a non-superconductive metal. This transition is so sudden, you see here, that it appears to be a transition to a different phase of matter. As I say, they have the ability to conduct electricity without the loss of energy. And as they travel through the conductor, they pass unobstructed through the complex lattice. So there are no bumps into, they cannot bump into nothing, and that's why no friction is being created, and they transmit electricity without any loss in the current or loss of energy. So a very, very interesting phenomena with several practical applications, such as shielding devices, medical imaging systems, infrared sensors, analog signal processing devices, microwave devices. And actually, it's very important for medical observations, biomedical observations as well. Okay, let's move to another phenomenon called paramagnetism. The permeability in such materials is much higher than the unit, and the susceptibility is about 10 power minus 3. What happens in these materials is that you have a weak magnetization, but it is aligned parallel to the direction of the applied magnetic field. And such materials are aluminum, platinum, or manganese. So they are slightly attracted by a magnetic field, but the material does not retain the magnetic properties when you remove the external field. So if you have a paramagnetic material, it will slightly be magnetized when you place it into a magnetic field, but when you remove the field, no remnant magnetization will be observed. And so this is what you can see a little bit how these paramagnetic materials are, the magnetization is randomly oriented. But once you apply a field, then it orients towards the external applied field. Once you remove the field, they will not retain any magnetization, and they will return back to the randomly state. So here we have, again, another schematic that shows this. You have no field, magnetization is 0. They're randomly aligned. You apply a field, they tend to rotate and align towards the field. So these are two phenomena that are not as important as ferromagnetism. Ferromagnetism is used for most of the magnetic sensors that are currently being used. And what is ferromagnetism and ferromagnetic materials? They exhibit a long-range phenomenon at the atomic level. And all the unpaired electrons, electron spins, will line up parallel with each other in a region which is called the domain. So what are the domains? These are regions inside a material, and they are magnetized in different directions, and the net magnetization of the whole material will be 0. So you have little regions, and that was discovered by Weiss in 1907. Within this domain, the magnetic field is intense. But in a bulk sample, the material will usually be unmagnetized because most of the domains will be randomly oriented with respect to each other. Maybe it's better if I show this to you. These are like the domains, and domain-domain interactions will result in magnetic domains being separated by these walls. Yeah, these are the walls that separate the domains between each other. This thickness of this wall will depend on the anisotropy of the material, but it's about 100 to 150 atoms span across on average. I don't want to go too much in detail, just to show you what is happening inside the domain. You have your ferromagnetic material. Before magnetizing it, this is how you see here the domains. The magnetization is randomly aligned. But then you apply a field, and the domains align parallel with the applied field. And this is how domains look after magnetization. And the external magnetic field can be imposed from a solenoid, an electromagnet, or even a permanent magnet. Now, what are the practical applications of such ferromagnetic? As I said, mostly in magnetic sensing. What happens is with ferromagnetics, in comparison to paramagnetic materials, for example, once you remove the field, they tend to remember their magnetic history. And this tendency to remember their magnetic history is called hysteresis. So you remove the field, there's still some magnetization remaining in your material. In order to bring this magnetization back to zero, you have to apply a field in the opposite direction. And this is called the coercive field. So we have the remanence and the coercive field that has to be applied in order to bring the magnetization back to zero. And all ferromagnets will have a maximum temperature above which they will lose their ferromagnetic properties. And this temperature is called the Curie temperature. So once you warm up your materials above this Curie temperature, it will lose their ferromagnetic properties. Now here you can see a magnetization curve of ferromagnetic materials. As I say, you have the applied field and the magnetization. You saturate your material, it cannot be magnetized anymore. And then when you remove the field, when the field is zero, you still have a remnant magnetization. And in order to bring this magnetization back to zero, you have to apply this coercive field. So if you remove the field, it does not necessarily mean that the domain structure will return to its original state. And here you can see what happens inside the domains when you magnetize your material. So you start from zero, they're randomly aligned, and then you magnetize your material, you bring it to saturation. The magnetization inside the domains has been aligned parallel to your material. Your material is being saturated, you cannot magnetize it anymore. Then you remove the field slowly, and what happens is there is still some remaining magnetization. And you see here, when you apply the coercive field, then you have again this randomly alignment of the domains, of the magnetization inside the domains. And if you go back again towards saturation in the opposite direction, then you have the magnetization inside the domains turning around to the opposite direction, in the direction of the applied field. So this is a little bit what happens inside the magnetic domains. Just to compare the two phenomena, when you heat a sample above its Curie temperature, it's a way to demagnetize it. So it will lose its magnetic properties once you heat it up above its Curie temperature. And this is called thermal demagnetization. Now we have an extremely interesting phenomenon which combines ferromagnetism and paramagnetism. And this phenomenon is widely used in biology or biomedical applications. And it's also very widely used in cancer therapy. And I'll explain you what happens here. These are nanomaterials. Your material is very easily magnetized when you apply a field, but as soon as you remove the field, it returns to its original state, so nothing, it doesn't have any magnetism remaining in it. So you can combine the easiness of magnetizing a ferromagnetic material and the fact that there is no magnetization remaining once you remove the field. So this way, these particles will not interact with each other. So you have no field, randomly aligned, you apply a field, they align towards the field, you remove the field, no remnant magnetization is stayed in your material, they return back to their original state. And here you can see if you have a paramagnetic material, this is how the magnetization occurs. But if you have a superparamagnetic material, there is no remnants magnetization. Once you're back to zero, you're back to zero. At room temperature, this is the most important, they have a much greater magnetic susceptibility per atom than the paramagnetic materials. So extremely ideal for applications where you need high magnetic susceptibility, so the easiness to magnetize your material, and you need zero magnetic remnants. I'll just quickly explain this because I think it's very interesting. There is a method called magnetic hypothermia to treat cancer. So they use superparamagnetic particles. And they insert these particles inside the tumor with an injection. And and they apply an external magnetic field. So by applying the external magnetic field, these superparamagnetic particles start to agitate and they heat up. And cancerous cells are very prone to temperature in comparison to the healthy cells. So it basically explodes, it heats it up, and the cancerous cells kind of explode. So you only treat the cancerous cells without destroying the healthy cells, because the temperature difference is quite high between the two. Once you remove your field, the particles don't aggregate with each other, and the fact that they are biocompatible and biodegradable, they can be discharged from your system, and you have no other side effects from this treatment. And it has been tested now in Berlin to patients with brain tumors, and it has been very, very successful. So this is a very important application of superparamagnetic materials. So I'm not going to go into details of this. How do you experimentally judge this superparamagnetism? You see that the magnetization curve exhibits no hysteresis, so no remnants is present, and the magnetization curve at different temperature must superimpose in a plot of magnetizations versus field and temperature. Now I'm coming to the end of the phenomena. So another phenomenon is called ferrimagnetism, and it spontaneously holds magnetization below this Curie point. But it will also exhibit paramagnetic properties above the Curie temperature. And such materials are ferrites or garnets. So you have opposing moments which are unequal, and they have a spontaneous magnetization remaining in this material. And you can use them in order to carry out experiments at very high frequencies, and they don't interfere with eddy currents. So you have a little bit of comparison between ferromagnetism and ferrimagnetism. So this is how the magnetization aligns when a field is applied in a ferromagnetic material, and this is the alignment in a ferrimagnetic material. So below the Curie temperature, at which the sublattices have equal moments, you result in a net magnetic moment of zero, and this is called the magnetization compensation point. And finally, the antiferromagnetism. You also see here a ferromagnetic material and antiferromagnetic material. This is the magnetization inside, opposing inside the domains, whereas here, when you apply the field, all the domains are being aligned towards the applied magnetic field. So these are all the phenomenon, the states of magnetic matter. And if you have a ferromagnetic behavior with the absolute value of one sublattice, magnetization differs from the other sublattice. So this results in a non-zero net magnetization. So what has to be kept in mind is if you have no external field, antiferromagnetic structure will correspond with a vanishing total magnetization. So this has been all the different state of matters. The most important, in my opinion, is the phenomenon called superparamagnetism, because it has very useful applications in biomedicine. And I would like to thank you so much for your attention. I hope it was quite interesting for you. And thanks so much for coming at this time.
Thank you for your overview of magnetic phenomena. Some of us will have some questions or remarks.
I would like to ask you, please explain.
Don't ask me astrophysics.
No. Just remind me exactly the major difference between ferromagnetics and ferrimagnetics.
Yeah. So basically you have, it's basically the magnitude of the magnetization. It's much smaller between a ferromagnetic and a ferrimagnetic material. So it will spontaneously hold a magnetization below this temperature. So you have opposing moments, yeah, as you see here. So you have opposing moments, whereas in a ferromagnetic material, the moments are aligned on the same direction.
So in this ferrimagnetism, the domains remain opposed until the Curie temperature. But they are small. Yeah.
Okay. What do you think about permanent magnets in general?
What do you mean?
Like in those things.
The biological applications of where you're supposed to stay stable if you have it here or you have this vest. That's what you mean. I have not yet understood how exactly at least the vest works. But I can kind of explain this because, I mean, we all have electric currents and every electric fields produced. And each electric field will produce a magnetic field. So I reckon that this kind of stabilizes the electric fields on your system. I don't quite know how the vest works, because when I try to see all the videos, I don't get the physics behind it. I've seen all these, like they present it, it makes miracles. People that have spine fractures, that they can walk with no problem. I don't know how this can happen. There is a possibility that it causes hyperemia, so like the blood flow is higher. I think it's called like that in English. It must be a Greek word. So the blood flow is quicker. So by having like a bigger blood flow on the spine, it kind of probably works sort of like a massage, where you have a greater flow of blood on these streams. But that the person with a fracture on the spine can walk, I don't know, just by wearing this vest. But I can assume that this is maybe a phenomenon that has been caused with a vest, a bigger flow of blood, because you have this application of magnetic fields pumping than the heart faster, and you have this flow of blood. My mom wears it, and she said nothing changed. And I told her, you have to believe in it. It's all in your brain. Yeah, she called me and said, shall I buy it? And I said, how much does it cost? And she said, well, it's cheap. I said, don't buy the vest because it's expensive. Just buy this and believe in it, and then you'll be walking just fine.
Some more questions?
I have one.
Why?
I'm just wondering, what is the temperature you need to rise up in the cancer cells in order to damage them? Do you know?
I think it's about between 37 and 40 degrees.
Okay.
But there has been a lot of research in the the material science behind it to lower it. In case the patient has fever and you have injected already the particles inside it, they can also cause the agitation without applying field. So they're trying to lower this below the 37 degrees. But cancer cells are quite up to 40 degrees. You can explode them, or you can destroy them a little bit and then also supply the drug, target it there, so you have this thermal agitation of the cells. You supply the drug and they die, hopefully without the patient dying.
There are no other questions. I thank you once more for your nice lesson.
Thank you very much for having me here. It was an honor.
Dovolím si vás pozvat na další přednášku, která bude za 14 dnů a bude mít doktor Setvák z Českého hydrometeorologického ústavu na téma meteorologické družice. Děkuji za 14 dnů.